Okay, welcome back, everybody. Okay, had a little bit of technical problem there. Hope everyone's doing okay. Any questions before we begin? What I want to do today is finish up 2 chapters, the rest of 7. We're about halfway through. And then chapter 8, which is nomenclature. And that's a pretty short one also. So if there are not any questions, I'm going to jump right in and continue where we left off. Okay. Now, what we've been doing here is we talked about the Lewis dot structures. We're going to actually start putting structures together. Now, we talked about Lewis dot structures for the atoms, which are pretty straightforward, and where you hold on one second. Where you just write the atom, find its position on the periodic table with respect to the A atoms, A metals or nonmetals, and then put a dot to represent the valence shell. Okay. Now we're going to start putting compounds together, and you'll notice that we're basically working with covalent bonds. Okay, that is compounds that are made up of nonmetals. And we're going to draw what are called Lewis dot structures. Now, the way we do that, we go back to the valence electrons. Again, outermost shell electrons, that's where all the action's happening. That's where all the chemistry occurs. And so when we start putting structures together, you're going to need the shapes table, okay? Because from this information, you'll be able to determine the geometry of the compound and give you. All right, so we identify all the atoms and then identify the number of valence electrons, okay, that each one brings to the structure. Okay, so we tally up the total number of valence electrons, okay. You'll be told who is the central atom. There's always going to be a central atom, and then everybody, whatever is bonded to it, okay, will be bonded to the central atom. Either the central atom will be underlined, or it will be in bold, or you'll be told in the question. Okay. As we start attaching everybody to the central atom, we keep note of the Octet Rule, in that the electrons that are being bonded to an element are shared between 2 different elements, or it could be the 2 same elements. But those shared electrons can count both toward either one of the shared atoms. So if I got a bond between, say, 2 carbons, that bond represents 2 electrons, and those 2 electrons are being shared between both carbons. Or it could be a carbon hydrogen, it could be anything of the sort, okay? So we go back and check the octet and verify that everybody has 8 electrons around it, either bonded or non-bonded. The exception is, remember, the hydrogen. The hydrogen only has 1 bond. Its rule is a duet, 2, like helium, okay? So you'll never find hydrogen with more than 2 electrons around it. So keep that in mind. All right, so then we identified, excuse me, we identified lone pair and bonding pair. But actually, that should be the last step. The last one here should be, if some of the atoms that are bonded together do not have the octet, but they have lone pair on them, we can take those lone pair and create a double bond between 2 atoms, okay? And we can continue to do that until we get a triple bond. Remember, that's the max, single, double, or triple bond. There's no such animal as a 4 quadruple bond, just single, double, or triple. And we do that until such time that we have shared, we're sharing electrons so that everybody has the octet rule fulfilled. Okay. Then at the end, we take an inventory to make sure that we have the same number of valence electrons total that we started off with in the beginning, because it's quite easy to lose electrons or even to add electrons as we're making these structures. So at the end, tally them up, make sure everything's okay. If it doesn't add up, then obviously something went amok, all right? All right, let's take, for example, water, okay? So you're given the formula H2O, okay? So it tells you here, unfortunately, it's not, oxygen's not in bold, but I will underscore it here. And oxygen is a central atom, okay? Now, we tally up, identify all the different elements in the compound. Obviously, we have 2 hydrogens, okay? Each hydrogen brings 1 valence electron, so hence 2 times 1, okay? Oxygen is in group 6A, and it brings in 6 valence electrons. So we tally up the thing, we got a total of 8 valence electrons to work with. These eight valence electrons are going to combine such that everybody, or by making single, double, or triple bonds, it's going to be put together in such a manner that the octet is fulfilled on everybody. Now here we got hydrogen. So hydrogen, make note of this, that it will only have 1 bond, okay? And then oxygen will have to have 8 electrons around it, okay? Hydrogen will only have 2 electrons around it, hence 1 bond, and whatever's left over will be around the oxygen. All right, so what I do here, since oxygen is the central atom, I very quickly just draw oxygen, okay? Then identify who's bonded to the central atom, and that is 2 hydrogens. So I can draw a line, okay? That line represents a bond between the oxygen and the hydrogen. Now, these 8 valence electrons, what I like to do is divide them by 2. Okay, first of all, when you finally get your valence electron count, it should be a number divisible by 2. If it's not, if it's an odd number, then something went amok, go back and check your math. But when I divide by 2, because I know that 2 electrons will give me a pair, so and I have either 8 valence electrons total to work with, or 4 pair, okay? The fact that I quickly put the oxygen in and 2 hydrogens took care of 2 pairs, okay? So now I got 2 pairs left over to work with, 2 pair of electrons, or 4 electrons. So then, obviously, we got 2 hydrogens here, so we can't put any more on the hydrogens. So the only logical place they must go onto will be the oxygen, because as is written now, oxygen only has 4 electrons around it, okay? 4 around it, so it's shy of the octet. So by adding those 2 pair, and I just draw 2 lines, I now have everybody happy here. The hydrogen, let's do a check, let's count to make sure we still have 8 valence electrons, and we got 4 pair all around the molecule. 2 of them are bonded, 2 pair are bonded to the hydrogens, and 2 of them are lone pair that are bonded on the oxygen, the central atom, okay? Now, I draw the line, but keep in mind, it is not incorrect to use dots. Okay, this is the same thing. I can use 2 dots to represent a bond. And then I got 2 dots here to represent the lone pair. Okay, notice I got a total of 8 dots, which is 8 valence electrons. My inventory checks out. I got 8 electrons total. I tend to like to put the line to represent a bond or a pair. And, you know, sometimes you might see diagrams that look like this, where they're using the line in combination with the dots, and that's okay too. All right, nothing wrong with either one of these 3 structures, right? Okay, and so now at this point, this is where the shape table comes in. Now we make a general formula denoted by A, B, X, and then E, I'm going to call that Y this time. Okay. Now, X can be a number for Vx can be a number from 1 to 4. Okay. And Y from E could be a number from about 1 to 2 for most 100%, 90-some% molecules out there. Okay. Obviously, if we got one E, we're going to have one less B, and vice versa. Okay. So then what A represents is the central atom. So we're always going to have an A, and it could be anything. Okay, that's why the general formula ABE. B represents what is bonded, what atoms are bonded to the central, keyword central atom. Okay? And E represents what are called lone pair of electrons to or on the central atom. Okay? We're only concerned about the central atom. Yes, there would be lone pair on other atoms outside. Don't care about those. Only concerned about is what is on the central atom. So if we look at water here, we'll see obviously we got A, okay? B are the two hydrogens. Now they don't have to be, I get this question a lot. Do B always have to be the same? The answer is no, okay? They could be totally different as far as type, which atom you're looking at, okay? But in this case, we got two total, regardless of what they are. There's two of them. And then we have E, because we recognize that there are lone pair right here, LP, lone pair electrons, LPE, okay? These are bonded pair of electrons, VPE, that's a good way to remember them. LPE being lone pair of electrons, not bonded, and BPE, bonded pair. Okay, they're bonded and being shared with another atom. Okay, and so we got two of them. So this guy, this general formula, this is our general formula for this molecule of water. AB2E2. Now, an important thing here, there could be a countless number of compounds out there with the same general formula. This is not unique only to water. There could be a countless, which means that those other molecules that share this general formula will also share the type of geometry, okay? So with this information, we go to the shapes table, which I hope you have downloaded and used and or be familiar with, and we get the shapes table right here, where we have the first column represents the generic or general formula, ADE, okay? The second column is the geometry represented by the general formula, and the third column is the name of that geometry. And then there is a bond angle. And this is the bond angle between whatever is bonded to the central atom. Okay, so what we just did was water, which is this one down here in the bottom, AB2E2. That is the generic or the general formula for the molecule of water we created. Next column gives you the geometry. Okay, and then its specific name is called bent. And then we have a bond angle between the two hydrogens and relative to the central atom of less than 109.5. Now, in general, the most common geometry out there in nature, our reference point, our little benchmark, is the AB4 geometry. And that is represented by the name of tetrahedron, okay? So that diagram there is kind of is trying to show you a picture three-dimensionally. Keep in mind, these structures, we live in a three-dimensional world, and even though we have to present this chemistry in two-dimensional, but it is three-dimensionally. You have two bees on the plane of the screen. You got one bee coming out of the plane of the screen, and another bee going back toward the back of the screen. This three-dimensional model, and its bond angle. Okay. Now, here's another thing to keep in mind is this. These lines here represent the bonds. Okay. We got 4 bonds at the central atom A to whatever B is, and it could be anything. It could be hydrogen, it could be chlorides, or any combination thereof. Okay. But there's 2 electrons in that bond. And those electrons, keep in mind, are negative charge. And so this one bond, this bond here will repel its neighbor and vice versa. And if those were like 4 springs and those were like magnets and the springs were magnetized, they will by itself settle out to this configuration, because that's the maximum repulsion. We got everybody far away from each other. Okay. And so just by default, that's the shape. Now what happens is this. We would think that this would be a trigonal or tetrahedral like the AB4. Okay. But there is a situation here. Now, instead of 4 bonds around the central atom, there's a lone pair on the central atom right there. That's what that represents. That little circle there is kind of just to show you it's a lone pair, okay, on the central atom. And not being bonded to anything, it tends to want to have more space. And so the result is these 2 electrons occupy more space, shoving that bond angle in. And one would anticipate that we would get 109.5 bond angle like we did up in tetrahedral, but because those lone pair occupy more space, they shove those 3 B's away, okay, and down, resulting in a bond angle that's less than 109.5, okay? Even though there's 4 moieties, if you will, around the central atom. It's just that one of the moieties occupies more space, and it shoves the rest of the moieties down, reducing that bond angle. And it's even more dramatic when there are 2 lone pairs, like the example we just did with water, and that now we got 2 lone pairs, okay? And you got 4 electrons out there that are not bonded. They're going to occupy a lot of space. So this bond angle really gets shoved in to be, it really should be like more like a double, much less than 109.5. So those lone pairs have a big effect. Those lone pairs on the central atom have a big effect on the overall molecule structure geometry. And on top of that, because of that more space that they occupy, it also has a big effect on the chemical properties, and the physical properties of the molecules. So we're going to learn more about that, okay, as we progress. Right now, we're just learning the beginnings of this, how to make the structures. All right, so now, this is basically what I just went through here with respect to water. And we end up with that particular structure, okay? Okay, you can see here that the octet around the oxygen is full, happy, okay? And around the hydrogens, we only got 2, we're good to go. You can proceed, and you can also see that we still have 8 valence electrons total. So a reminder is whatever valence electrons you come up with in your addition up front, step number one, that is what you got to work with. That's what you got to make work. Okay. Now, let's try some here. Okay. And obviously right now, you don't know what the structures are, and that's okay. Okay. But you're given all the atoms that are in this structure, and you're given the general formula. There's nothing about the structure here. You're just given the general formula. For example, you got carbon that is bonded to nitrogen and hydrogen. Carbon is underlined, it's a central atom. And then obviously you've got two nitrogens bonded to it. Same is true to the second one. It's carbon, hydrogen, and 3 fluorides, okay? So carbon's a central atom, right? We got 1 hydrogen, 3 fluorides. The third one, we got carbon again, is a central atom, and then bonded to it are 2 oxygens. And then finally at the end, we have nitrogen as a central atom with 3 hydrogens bonded around nitrogen. So let's take the first one, and let's first of all do an inventory of the valence electrons that we have to work with. Okay. All right. We have hydrogen here, and I just make a note of it. I got one valence electron. Okay. All right. Carbon. Carbon is in group 4. Okay. So it has 4 valence electrons. And then nitrogen is in group 5, so it brings to the table 5 valence electrons, okay? So we tally this up, we have a total of 10 valence electrons or 5 pair to work with. 5 pair to work with. All right, so that is the number we work with. We can't change that number. That is what every one of these atoms brings to the table. All right, so the fact that carbon is the central atom, we can very quickly write carbon and essentially draw a line for nitrogen and a line for hydrogen, because we know, given what we're given, that hydrogen and nitrogen are bonded to the central atom. Now, what that does is take care of 2 pair. So now I can subtract 2 pair from the 5 pair I calculated, and I got 3 pair to work with, okay? Now, obviously, I cannot put any more on hydrogen because hydrogen is happy now and is stable now because there's 2 electrons around it. Its duet has been fulfilled. So this 3 pair cannot be put on hydrogen. We look at carbon. Carbon only has 4 total electrons, or 2 pair, right? And nitrogen only has 1, right? So the point being is carbon and nitrogen both are going to need 8 eventually. So these 3 pairs you can put anywhere you want. Now, my personal choice is I start from the outside atoms and I work in. And if you can play with it and figure out what works for you. It doesn't make a difference if you start inside or outside. Keep it in mind, I cannot put more than 8 total on any atom. Okay. So I'm going to very quickly put those 3 around nitrogen. So that took care of 3. So now I've used up all of my 5 pair. Go back and do an inventory to make sure you still got 5 pair. 1, 2, 3, 4, 5. I still have 5 pair. I didn't add by mistake any more. I did not take out any more. Okay. All right. Now go back and check the octet. Nitrogen now is happy, right? It's stable. It's got 8 around it, 1 bonded and 3 lone pair. So you got a total of 8 around nitrogen. But look at carbon. Carbon only still has 4. Okay. And hydrogen obviously is okay. So hydrogen's out of the, we don't have anything to do with hydrogen. Okay. So the point is this: we got lone pair on the nitrogen that we can bring in to make double bonds or a triple bond. Okay. So if we think about it, since carbon is short 4, I can take a pair here and share it with the carbon, and another pair here and share it with the carbon to make a triple bond. Okay, so what I get structurally is this: carbon, hydrogen, carbon, and then those three pairs that I made a triple bond. Okay, and that's what I made right there. Now go back and count, check your inventory. All right, I still got 5 pairs. So it may seem that I created pairs someplace, but I did not. All I did was take a lone pair from one atom and brought it in to share with another atom, okay? And in this case, I took 2 lone pair and shared it with carbon to make a triple bond. I still got 5 pairs, so my inventory is still good. Okay, now I go back and check my octet. Okay, nitrogen still has 8 electrons around it, but now 3 pair are shared with the carbon. In the beginning, 3 pair were on the nitrogen. Now I got 3 pairs shared with carbon, and there's 1 lone pair on nitrogen. Point being, there's 8 electrons around nitrogen, so nitrogen's okay. We already did hydrogen, we're aware of that. So let's go check carbon. Carbon has 1 pair that is shared with the hydrogen and 3 pair that are shared with nitrogen. So carbon is also stable now. So that is the structure of what we have. And now I can write the general formula, okay? And the general formula is A for carbon and B2 for what is bonded to the central atom, meaning there's 1 hydrogen and 1 hydrogen. So our general formula is AB2. Hopefully you can see that this is what we call linear, okay? And we'll go to the shapes table to verify that. Okay. Call that up, shapes table, AB2. And there it is right here, AB2, okay? And to recall, we have hydrogen, carbon, triple bonded to nitrogen, and then that lone pair, okay? Here's our central atom, there's the nitrogen. That bond angle between the nitrogen and the hydrogen is 180 degrees, and it has a shape called linear, okay? Which is also the same with the AB, meaning the central. There's really no central atom when there's only 2 atoms. Either one could be central, but when there's only 2 atoms bonded to each other, by default, it's linear, okay? There's really no bond angle there because there's only two atoms, 2 atoms bonded together, and that's it. But the common thing is it's linear where there's 2. And if you add another B, it's also linear. And that bond angle, now you have a bond angle of 180 degrees, okay? All right. So that's the structure that we have. And we also named the geometry. Okay, let's do the next one. All right, we have carbon, which again has 4 valence electrons, right? We got 1 hydrogen, which is 1 valence electrons. And then with the fluorides, we got 3 of them, right? 3 of them, and each one brings 7, does it not? Groups, fluoride, there's 3 fluorides, each one brings 7. That's a total of 21. Check my math, keep me honest here, okay? And so what we have a total of is 4, 5, 6, okay? We have 26 valence electrons, or guess what, 13 pair. That's why I like to work with pair. Numbers are getting big. You can go up to 32 or even more depending on your structure. Okay, so that's what we got to work with. We know that carbon is a central atom, so I can very quickly notice that carbon has 4 bonded species. It has 1 hydrogen and 3 fluorides, so we can very quickly draw 4 lines and put the hydrogen and the fluorides on. Okay, so that took care of 4 pair, right? So minus 4, we have 9 pair of electrons left over. Now the excuse me. Now the question is this: where do I put that 9 pair? Well, let's look at the structure we just drew. Hydrogen, we're good with hydrogen. Okay, the rule is 1 pair, 1 bond. That's it. Can't add any more. Look at carbon. Carbon has 4 bonds around it, which is a total of 8. So carbon is fine. I cannot add any more. Remember, I can't. The magic number is 8. Okay. I see a lot of central atoms with 10 and 12 electrons. That's totally incorrect. You gotta adjust the electrons so that everybody, regardless of where they're at, has 8 electrons around it. Okay, since carbon is done, the only logical place they must go is around each of the fluorides. Okay, I got 9 pair to work on. So here I go. I got 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so that took care of that 9 pair. I got 0 pair left. Okay, let's go back and double check. Okay, we had 9 around the fluorides, 10, 11, 12, 13 around the carbon. We're still good. Okay, still good with lone pair count at 13 pair or 26, whichever you want to do. You know, some people do. This is why I like the lines. Okay, because you can see already there's a lot of dots being written. And if you prefer to write dots, feel free, you're not incorrect. But it's a lot of dot writing. Okay, so these 2 structures, left and right, with the line and with the dots, are the same thing. Whichever one you want to present, if you have to present something, is perfectly legitimate. Okay, so with this, now we need the general formula. Okay, and so we have A, which is carbon, and then B, which is the items bonded around carbon, which happens to be 4. Note that there are no lone pair on the central atom. So that is our general formula, AB4. We take that information and we go to the shapes table and we look for AB4. And here it is right here. That is our benchmark, AB4. And its name is Tetrahedron, and it is a bond angle 109.5. Okay. And so if you can imagine the carbon here, and then maybe one of the fluorides there, one of the fluorides there, a fluoride there, and the hydrogen there. Yeah, this is one of the general halides. We call these halides. You get up into the UV and cause all kinds of headaches with their ozone. Okay, so let's go back. And there's the structure, okay? Tetrahedron. All right, here's an interesting one, carbon dioxide. Okay, so here we go. Carbon, again, 4 valence electrons. We have 2 oxygens. Now, oxygens are in group 6. Okay, so that means we have a total of 12 valence electrons, right? Check my math, double check me. Okay, so I got group 6, there's 2, and that's 12. 1 carbon, group 4, right? I got 16 valence electrons, or 8 pair. Okay? This is not 20, this is oxygen here. 2 oxygens. That's times 6. Okay, we got a pair. Carbon is the central atom, so we can quickly write that. Then we got two oxygens bonded around the central atom, and we can do that. And guess what? That takes care of 2 pair. So we got 6 pair left to work with, okay? And so like I stated earlier, I like to go on the outside atoms and work my way in. There's no hydrogens here to worry about. It just, all of them are going to require 8, all the atoms here. So I'm just going to go around the horn. So I go 1, 2, 3, 4, 5, and 6, okay? And then the 2 I had before, so I still got 8. So I still have 8 pair, okay? I did not lose any, or nor did I add any. Now, if you ever get yourself in that position where you got extra valence electrons and you see that everybody has the octet fulfilled, the hydrogen's happy, then obviously something went amok and it's probably somewhere in the map. Go back and check and verify that in fact you got the correct number of valence electrons. And the opposite is true. You go through this exercise and you end up with not enough electrons. No matter what you do to try to make triple bonds and when it doesn't work, then more than likely your math went amok someplace. Go back and check your valence electron count. All right, so here, that's our initial generic formula at this point. We go back and check the octet. If you look at it, each oxygen on each side is okay. We got 8 electrons around each oxygen, okay? Look at the carbon. Carbon's only got a total of 4 electrons, 2 pair, okay? So what do we do? Like we did with this one over here, we're gonna take some of these lone pair and create double bonds. Now, the nice thing about this setup is this, that both electrons each have extra, both oxygens each have extra electrons, that we can take 1 pair from 1 electron and 1 pair from a second oxygen, and create a double bond, resulting in this structure where we've got carbon double bonded to oxygen on the right side. We still have those 2 oxygens, and then on the left side, we got carbon double bonded to the oxygens. And go back and count. 1, 2, 3, 4, 5, 6, 7, 8. So we still got 8 pair when we wrote a structure here. And we can see that everybody's happy now, okay? We have 8 electrons around everybody, 8 around the oxygen, 8 around the carbon, and 8 around both oxygens from both sides, okay? So 2, 4, 6, and 8 for this oxygen on the left, 2, 4, 6, and 8 for the oxygen on the right, and then 2 double bonds for the carbon. They're happy, okay? Now you might ask the question, what if I go the other way, and I instead of one side of the electron, one side of the oxygens, I leave it alone and I create a triple bond on the right side? Well, this is what's going to happen. Okay, let's do this scenario where you have created this scenario. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and you triple bond. Well, what this does, unfortunately, which is beyond the scope of 130, we were doing this in general chem, we will see that we end up with a positive charge on this side and a negative charge on this side, but we're not going to talk about it right now. This structure has been brought up before, and technically it's not 100% incorrect, but if with a triple bond to the oxygen, because if you look at there, everybody's happy here. For us here at 130, I wouldn't utilize it. Okay, if you move on up, in chemistry, that's a legitimate structure, and it's not very stable, but it's legitimate. But I would try to make it so we end up with this structure right here, like this, okay? Because eventually what this is temporarily, this will move into this because this structure is a lot more stable, okay? All right, so with that, we have the general formula of AB2, okay? And I'll leave this part left to you because it's very similar geometry as HCN, okay? And that is a linear, and its bond angle will be 180 degrees. All right, so there's the structure. Now, we're going to learn about polarity, and that is when we have unequal sharing of a bond. And we have that here with the carbon dioxide we just did. Each bond is shared, it's a covalent bond, but there's an unequal sharing that creates what we call a polar bond. And the same is true for the HCN and the fluorinated hydrocarbon here also. And that results in giving it some specific property. And so we're going to talk about that property, but in order to determine that property, guess what? We have to come back to the Lewis dot structure so we can visually see it and be able to predict what that property will be based on the geometry and the structure of the compound. Okay, so that's why this part is important with respect to figuring out the geometry, which then gives us insight as to what type of property they have. Okay, all right, excuse me. So now the last one, we have nitrogen and 3 hydrogens. Nitrogen is group 5, so we got 5 valence electrons, and we got three from the hydrogen, so we got a total of 8 valence electrons or 4 pair, okay? Now, nitrogen is the central atom, so I can very quickly write down nitrogen, and then there's 3 hydrogens bonded to the central atom, and so I can quickly write 3 hydrogens bonded with a single line, okay? So that takes care of 3 pair. Guess what? I got 1 pair left. Well, again, we have 3 hydrogens. I cannot add any more on that because adding a hydrogen, a pair of electrons on the hydrogen would violate its duet rule. So the only logical place to put it, obviously, is in the central atom, okay? All right, so now you go back and check. That takes care of that valence of the 1 pair. We got 0 pair to work with. Go back and do your inventory, double check, make sure you still have 4. You got 4. So 4 pair, we're still good to go. And that's it. That's the structure. Okay. You don't have to make any, because the octet's fulfilled with respect to nitrogen. Okay. It's happy. And the hydrogens. The hydrogens are all set with its duet. All right. So now we find the general formula. And that would be B3, right? Got 3 hydrogens here. And then we have a lone pair on the central atom. So we have a B3E. And that is our general formula, which then we go to the shapes table and we search AB3E, and there it is right there. Okay, and its name is Trigonal Planar, and its bond angle is much less than 109.5. Here's that lone pair on the center. This could be nitrogen sitting here, and here are the 3 hydrogens around it. Okay, and again, the lone pair sitting on top of the central atom take up a lot more space, so they shove this bond angle in, making it much less than 109.5. Okay. Now, there's a specific bond angle for that, but we're not going to get into that. We just simply call it less than 109.5. Okay. One thing to keep in long-term memory when we're coming up with structures here. and that is this. We had talked earlier about, I mentioned earlier about something called polarity, something that's polar, or at this point, the way to look at it is this: something that's water-like and something that's oil-like. Okay, we all know that oil and water do not mix. Okay, you don't believe me? Look at your bottle of Italian dressing. You got 2 layers there. You got your oil dressing and your aqueous layer. Okay, now when we talk about polarity, when something is polar, it has water-like properties. Okay, when something is non-polar, it has oil-like properties. But right now, that's going to be our definition to put it in perspective. And so the thing to remember is whenever you come up with a structure that ends up with a lone pair on the central atom, you will always have a polar molecule. Okay, so this one we just did, I could predict to be very polar, and certainly it is. It will be. Water, for example, remember we did water, had 2 lone pairs. This structure down here, let me clear this up a little bit. Water has, this is the structure for water. There was AB2E2, 2 lone pairs on the central atom, which is oxygen, and water is it's the most polar species we have. Very polar, again, because the lone pair being on the central atom. And that will help you, if you keep that in mind, down the road when we start determining the properties of molecules. Once we get the atoms that we're working with, when we make the molecules, the next thing we're going to do, we're going to predict the polarity of that molecule. Okay, and to get that information, we got to look at the structure. Okay, so that's why this part here is why we're going to this part. All right, and that would help us down the road to do relative comparison of properties like boiling point. Why does this molecule have a higher boiling point than this molecule? Things like that. And we'll be able to predict that strictly on the structure that we have here. All right, with that being said, here's the formula that just came up. All right, now I'll go ahead and give you these names. Make it HCN is hydrogen cyanide. It's very poisonous gas. Yeah, Triflural Methane is the second one we just did, which we're not, you probably won't see this, carbon dioxide. And this, I'm sure you probably smelled it. Okay, that is the formula for ammonia. A lot of cleansers, window cleansers have that ammonia odor. That is what you're smelling, ammonia. Or if you got dirty diapers around the house, there you go. All right. Okay, so this is what we just went through with respect to HCN, kind of break it down. Creating double bonds, we went through this scenario, 5 pairs of electrons, and then we made triple bonds such that everybody is filled. But keep this in mind. When you're finally done with making whatever bonds you need to make, go back and do a check to make sure you still have 5 pair. In this case, 5 pair, or whatever pair you calculate. Okay, you don't want to lose any, and it does happen. When you get a lot of electrons, you kind of miss one, or you may add some by accident. So check, make sure. Okay, now polyatomic ions. Now, what exactly are these? Well, let me refresh your memory. I did introduce them to you right here. Okay, on the periodic table, we have most common polyatomic ions. At that time, I stated these guys. First of all, if you notice them, they are all covalent, meaning that they're just nonmetals bonded to each other. But they end up with a charge. They do have a charge, making them ions, okay? And the aspect I told you before when I introduced these is these are units. They stay together as units. For example, the first one, NO3, called nitrate, okay? if I ever need to add more than one nitrate, let's say I need 2 nitrates, okay? I would not do this. Let's say I need 2 nitrates. So that means I need 2 nitrogens and 6 oxygens, okay? Well, that's not the case. You don't do that. What you do is you put the nitrate, in this case the nitrate, in parentheses, and then the subscript here will be the number greater than 1 that you need. Sometimes you need 1, you know, no parentheses, you can need 2, 3, or whatever number you need. But these units remain intact. They don't separate, okay? You keep them intact. Now, what we're going to do is we're going to determine the Lewis dot structure for these polyatomic ions. The procedure is the same. You count up the valence electrons, but then there's an additional step, and it depends on the charge, okay? If it's a negative anion ion or a cation, which in this case we only got 1 to worry about, okay? We have to add or subtract that number of valence electrons that we calculated. Okay. Now, we're not adding electrons to it. What is happening here we have to take into account that an electron was either bound and used up with something else, and so we have to account for that by adding the number or subtracting the number. All right, this will make more sense here once we go through a couple of examples, and then I'll show you. Now, the other aspect is keeping track of knowing the charge. Then, when we draw the structure, we end up with the same general formula, ABE, okay, which will give us the geometry of it. And then we put a bracket around it with the charge to designate it as a polyatomic ion. And we'll do some examples. All right, let's take one. Well, before that, we have to do some changes. Right, if the polyatomic ion is negative, looking at that charge, if it's a -1 or -2 or -3 or whatever charge it is, we're going to add a number to your final valence count, valence electron count. If it's a positive, we need to subtract a number because those electrons have been tied up. And we're not subtracting electrons, but they've been tied up and bonded somehow. For example, we just did ammonia. Okay, and we're going to learn about this when we talk about acids and bases. The fact that it had a lone pair here, okay, what it can do, it can bind with a hydrogen that's roaming around. The result is that we end up with a positive. This is the ammonium in the polyammonium ion. That electron that was there initially, lone pair in the centrion, is still there. It's just being tied up with a hydrogen, all right? The fact that it's being hydrogen, we have to account for the hydrogen. So whatever number we come up with, we have to subtract. We have to subtract the number because that hydrogen that came in did not bring in any electrons. It used the electrons that the nitrogen already had. Okay, so I just want to make that clear. We're not really adding or subtracting electrons. We're adding or subtracting to keep the accounting straight. That's all we're doing, to keep the accounting of the valence electrons. All right, so that being said, we put brackets around the whole picture, all right? And let's try ammonia. Nh3, that's the first polyatomic ion, the only cation there. We do it the same. 1 nitrogen's in group 5, 4 hydrogens is in group, again, each hydrogen brings in 1. And there's 4, so we have a total. If we were not to subtract this, imagine it, we would have 9 valence electrons. That right there is a flag because all the numbers should be divisible, should be even numbers, divisible by 2. Okay, so if you end up with an odd number, then you got to look and refresh your memory. Do I add or subtract a value? Okay. So in this case, it's a positive cation, so we're subtracting 1, so we have 8 valence electrons, okay, or 4 pair. Now, the nitrogen is a central atom, and so we have nitrogen, and we got 4 hydrogens around it. So it's taking care of all that. And then we have, it's a polyion, so we put a bracket around it with the charge on the top right side. Okay? So that's what we mean by put a bracket. Put a bracket, not parentheses, but a bracket, and then a charge on top. Now, if we needed to do the general formula, we can do the same thing. The general formula would be AB4. And I'll let you look up AB4. It should be tetrahedral. So that polyatomic ion, the ammonium ion, okay, would have an AB4 geometry, which is tetrahedral, okay, with 109.5 degrees bond angle between all the hydrogens. Okay, and there you go. Here's a better picture in mine. All right. Now that is for the cation, which again, I stated we only got one. Let's do these. We got BrO3 with a negative charge. Okay, the bromine is group 7, so it brings in 7 valence electrons. Okay, there are 3 oxygens, each of them bringing in 6. All right, it's got a negative charge, so what we do, we add 1. Okay, when it's positive, we subtract. But we add 1 and we tally that up, and we have a total of 26 valence electrons, or 13 pair. Now, once that is done, you can very quickly draw the structure, no different than before. The Br, the bromine, notice is not the bromide, but the bromine is a central atom. Okay, and then we have 3 oxygens around it. So we can quickly bond 3 oxygens through the bromine. So that took care of 3. So we got 10 to work with, 10 pair. And like I stated earlier, I start from the outside atoms and work my way in, keeping track of my octet. So each oxygen needs 3. So I can go 1, 2, 3, 4, 5, 6, 7, 8, 9. That took care of 9 pair. I got 1 pair left. Okay, the oxygens are all happy. The only place that 1 pair can go, obviously, is in the bromine. Okay. And so now double check my 13 pair. Everything's there, 13 pair. At the octet around everybody, it's there, so everybody's good to go. I just simply put a bracket around the whole thing and my charge on top. And there it is. And now my general formula, if I need it, would be AB3. There's a lone pair on the bromine, so that would be my general formula. Okay. Same general formula geometry as ammonia. Okay. All right. And we end up with that. Okay. With the AB3E. All right, SO4, this is a sulfate, polyatomic ions. You'll find that in foods a lot. If you read your labels, you'll see your preservatives, sodium sulfate, sodium sulfite. Anyway, sulfur is a central atom. We got 4 oxygens, and there's a -2 charge on that. So we got sulfur brings in 6 valence electrons, oxygen brings in a total of 24. Okay, it's in group 6, and there's 4 of them. That's 24 valence electrons. Okay, then we add a 2 for the -2 charge. And so now we have a total of 32 valence electrons or 16 pair. Sulfur is the central atom, so I can very quickly write the sulfur. There are 4 oxygens bonded to the central atom. I can bond that, and that takes care of 4 pair. It leaves me with 12. So obviously the only place to go, because it looks like sulfur is happy here. Now we got 8 around sulfur. So the others, 12 have to go around the oxygens, right? Each one's going to take 3. 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10, 11, and 12. That's 12 around the oxygen plus the 4 we already had. Okay, that took care of 12. We still have a total of 16 valence electrons. That is the structure. We put the bracket around it. Okay, it's got a -2 charge, top right corner. And if we need the general formula, guess what? We got AB4, okay? A is the sulfur and the 4 oxygens around the sulfur. So its geometry would be, you can look this up to verify, it's tetrahedral. They would have a tetrahedral geometry. All right, let's clear that. And we got that. Okay. This originally, and we're going to learn about this, this originally came from an acid, H2SO4, okay? This is sulfuric acid, one of the acids we're eventually going to talk about. And when an acid reacts with the base, it loses its protons, and when it does that, it becomes sulfate, okay? Remember, and I state that because remember the one we did earlier with HCN, which is again an acid with hydrogen. When we react HCN with a base, like hydroxide, for example, we end up with this species right here. This is called the cyanide ion. Okay. All right, which again also is poisonous. All right, carbon brought in 4, nitrogen had 5. And notice if we just stopped here and forgot about the charge, yeah, it would have a number of 9, and we wouldn't be able to continue because we have an odd number. We're going to go back and check, but I'm missing something here. So we got to subtract, add 1, excuse me, okay? Gives us 10 and 5 pair. And if we go through that scenario like we did before, here's your 5 pair. Before we had the hydrogen was bonded to the carbon and it was tied up. That lone pair on the carbon was tied up with the hydrogen. Let's say, for example, up here, and this is for example, you forgot and what you did was 4, 5, and you subtracted 1 instead of adding 1, right? So you end up with 8, okay, or 4 pair. All right, well, you got 4 pair and you start writing the structure. I go carbon and then nitrogen, then that takes care of 1. So I got 3, 1, 2, 3. So there's 4 pair, but regardless of if I make a triple bond, I don't have, if I make a triple bond, so like this, I still don't have enough electrons around carbon. And I can't make a quadruple bond, like I stated before. You can only go up with triple bonds, okay? The geometry makes it very, very difficult to make quadruple bonds. And so that, when you end up with something like this, should tell you, oh, maybe my error was here, okay? You end up with a scenario that you don't have enough electrons. You know, even though you're counted 4 pair, I got 4 pair, but I don't have enough electrons to make the octet around all the atoms. So that means there should be a flag to tell me I did something wrong. And the same is true in the opposite. When you have the positive and you added a number instead of subtracting a number, you have too many electrons and you can't put them any place. Keep it in mind in the octet and don't, okay? So, all right. All right, so this particular part, I've already introduced to you the concept, and they call it the valence shell electron pair repulsion, or VSEPR. And that is nothing more than the electrons have a negative charge. And if I get electrons, especially lone pair electrons, or any electrons, bonded pair, they're gonna repel each other such that they're going to get away from each other as far away as possible. That results in a specific geometry, okay? So depending on how the electron bonds are put together relative to each other will determine the structure, okay? Because the electrons are repelling from each other. They want to get away from each other. So they're going to adjust themselves so that they maximize their repulsion given their geometry. And that, in effect, affects the properties of molecules down the road, okay? So a lot of this I've already talked about. We talk about the ABE, which A is the central atom, B is the outer atoms. They could be the same or different. And then E represents any lone pair in the central atom, okay? So when we only have two atoms, it's pretty straightforward. It's linear, okay? So all of the diatomic elements, like hydrogen, oxygen, nitrogen, have that geometry, very linear. When we have the AB2, that also is linear. We did carbon dioxide, okay? And their geometry 180 degrees. We can put a degrees here because when we get the bond angle, we're talking about what is bonded to the central atom relative to each other. Obviously, when there's only two, there's, just only two people there, so to speak, two moieties. Here we got three, so you got to have at least three to get a bond angle of some sort. Okay. The next one, the AB3 geometry is trigonal planar, where you have the central atom, and then it's flat. If you can look at this, it's basically just planar, flat, and three-dimensional, 120 degrees all the way around. This example is a formula for formaldehyde. You may be familiar with that. Formaldehyde was utilized for in science when you're cutting up a pig or whatever, and it's been stored in formaldehyde. You try not to use it as much anymore because it does cause cancer. Tetrahedron, I talked about that. We get the central atom and you got four moieties, the same moieties, and they could be the same or different, it depends. And here's a two-dimensional model of it. And this one here is methane. This is a hydrocarbon, carbon in the middle. It's the smallest hydrocarbon we have, where you got one carbon and four hydrogens bonded around it. Now here's an interesting one. You got SO2, and if you were to compare that with the formula of, let's say, carbon dioxide, you might be tempted to do like we just did with carbon dioxide and call it linear, but keep in mind that carbon is in group 4 and the sulfur is in group 6, so you're bringing in more electrons. So when you go through the exercise of figuring out the structure, guess what? You end up with a lone pair in the central atom. And what's going to happen is it's going to shove that bond angle, which we thought it would end up at 120, like the planar one, but much less, again, because that lone pair occupies more space, okay? So that lone pair, plus the fact that it's got a lone pair on the central atom, you have a very polar species here, okay? Because of the geometry. So this is a AB2E, which is called the Bet geometry. And then we did ammonia, which is the trigonal pyramid, where you have in the central atom, you have the lone pair again, all right? And because the lone pair on the central atom, you're going to have a very polar species. Plus, that bond angle is going to be much less than 109 because those lone pair again are occupying more space and they're shoving everything down. And then water we went through, that has the AB2E2 geometry, very bent. That should be like a double less than 109, because with two pair, a lone pair in the central atom, that bond angle really gets shoved down. Almost probably close to 90 degrees, not quite though, but close. Okay, so to summarize all this, okay, given a compound or a polyatomic, specifically a covalent compound, because bear in mind the ionic compounds, they're not bonded. They have no factor here, okay, when figuring out the structure. But if the covalent compound or a polyatomic ion, because again, polyatomic ions, even though they have a charge, they are made up of covalent compounds, okay, covalent bonds. Be able to draw the electron dot structure, and from the shape table, be able to determine the shape and bond angles, okay? And you may want to try this as a fun thing to do, is try the compound pH3, okay? And give you a hand to shoot. It's the same group as nitrogen. So if you replace that phosphorus with nitrogen, you get the same geometry, okay? And then the fun one is ozone. You're all familiar with ozone. There's two types of ozone out here. You got the ozone because it plays havoc to your health. If you're having breathing issues, it's out here, down here in the lower atmosphere with us. It's what we emit, and it causes all kinds of problems. But then you got the good ozone, which is kilometers up in the sky, that interacts with the UV light coming from the sun. And if it wasn't for that, the UV radiation that we would be getting would be much greater. Problem is we have a big hole up there and it's a small layer, very small layer has been calculated, but we punched a hole in it because of these fluorinated hydrocarbons, like that example we did earlier with carbon 3 fluorides. They go up there in the upper atmosphere, interact with UV light, and destroy the ozone. But it's getting better. We removed a lot of the hydrocarbons. They used to use them as propellant for your air conditioner or hairspray, things like that. We're using a little bit different types to help out the atmosphere. Okay. Now, which brings us to, we talked about drawing these bonds, okay? And now we're going to jump into bond polarity. We had talked about, I mentioned to you that there's two types of bonds, or properties. I say something that's polar-like, something that's non-polar-like, something that's water-like, something that's oil-like, okay? Those are the general, kind of give you a picture of what I was talking about. Or get into more detail here. Now, for some reason, polarity seems to be a challenge, okay, students in the beginning. But I've attempted to, give you an idea here that a general way to look at this to help you define whether a bond is polar or non-polar, okay? What we mean by non-polar is that when you get a bond that's equally shared, those electrons are equally shared, then you have a scenario like this, okay? Where let's say a generic formula, A, whatever A could be, bonded to another A, okay? Well, what they share is this. One, the En, remember that property, the electronegativity? Remember electronegativity, which is a measure of the affinity that an atom has for electrons when it is bonded to something, bonded atoms. And so we use fluorine as our benchmark. On the periodic table, fluorine is over here, and that is the most electronegative species out there. So when it's bonded to whatever other than itself, it's going to pull the electrons dominantly, okay, toward itself. Okay, it won't take them away, but it'll pull them very tightly. Now, every atom on the periodic table has their own electronegative value, and you're more than welcome to memorize them all, but it's not necessary because we use fluoride is our benchmark. And if I want to compare two atoms, I look at their position relative to fluoride, and whoever is closer to fluoride has a higher electronegativity, which then tells me in which direction the electrons are being pulled in a bond. Obviously, AA, whatever AA is, they're both the same. So I got two people here, same weight, same strength. The tug of war between the electrons is the same. It's equal. So we have a non-polar bond, okay? And by meaning polar is we're going to put, there's things around you that are polar. The Earth is polar. We have a north side and a south side. If you're running off batteries right now, in whatever electronic device you're using, that battery is polar. You got a negative side and a positive side, okay? And so what's happening here in this bond, when they're polar, we're gonna make a partial, what we call a partial positive side and a partial negative side, simply because of who is pulling who with respect to the strength of the electronegativity of that atom, okay? So A and A, meaning they're both the same, we're going to get an equal sharing. Now here's another bond that I want you to put in long-term memory. Carbon, hydrogen, okay? All carbon-hydrogen bonds, because their electronegativity negative value is essentially the same, are considered non-polar bonds, okay? Let me repeat that. All carbon-hydrogen bonds are considered non-polar bonds. Okay. Now, we'll come back to the electronegative, the periodic table in a second. Whenever we have A, and now it doesn't make a difference who is bonded to, but it's not an A, it's a B. We have a polar bond. Straightforward. Don't have to go any further. Okay. The only exception is the carbon-hydrogen. Okay, the carbon-hydrogen, two different atoms, but their electronegativity is basically the same, so we consider that as non-polar. It's the same. Okay, so over here on the left, we have all the diatomics. All the diatomics are non-polar. Carbon-hydrogen is non-polar. Okay, on the right side, that means that everything else bonded, covalent bonded, is polar. Okay, the question is, all right, now that we know it's polar, so where do we get just from this information is this. If I have an AA bond, it's less likely to dissolve in water than if I had an AB type of bond, because an AB bond would be a lot more polar and therefore share polar properties in the solvent like water. Water is our reference point, oil and water, right? Okay, now the question is, in which direction does this pull go to when I'm looking at A and B? And the answer is, it depends on electronegativity and its relative position to fluoride. So let's do a carbon-nitrogen bond. Okay, automatically, carbon-nitrogen. It's an AB scenario. It's a polar bond, plain and simple. You don't have to go any further. You don't even have to analyze any further. It's a polar bond simply because they're different atoms and they're not carbon-hydrogen, okay? So now the question is, how does that, who's pulling who? Who's stronger? There's going to be one is going to be stronger than the other. Well, to answer that, we go to the periodic table, and carbon's about right here. Nitrogen's about right here, okay, on the periodic table. So that tells me that nitrogen is a lot more electronegative than carbon. So then tells me that in this bond, carbon-nitrogen bond, the nitrogens are pulling the electrons onto itself much greater than the carbon. So what results in is we draw an arrow. The arrow points to the most electronegative element, which is nitrogen, and then we put like a little plus at the end of the arrow, and that's on the carbon side. The result is this. On the nitrogen, it produces a partial negative. That symbol delta, that's lowercase delta, that means a partial negative. And on the carbon side, it creates a partial positive. Not like ionic compounds. Here's where we got to get the difference here. Ionic compounds have a full positive and a full negative. Okay, the electrons are stripped away from one atom and given to the other atom completely. And then when they come together, like sodium chloride, they attach each other like two magnets because full positive and full negative. In covalent compounds, it's not stripped completely. It is pulled, resulting in less electron density around the carbon and more around the nitrogen, resulting in a partial negative and a partial positive, which this, ladies and gentlemen, is a very important property in chemistry when we're trying to make new compounds. Without this polarity, it would be very difficult to make new compounds because we tap into areas like this in the molecule so we can do reactions in that area. Otherwise, we have to figure out how to do it. Sometimes it's not possible with the technology we have currently. So anyway, that's why we can make so many different antibiotics that are based on penicillin, because we can go into the structure of penicillin, look for polar bonds, and make changes there. Sometimes a new compound we make is better than penicillin. Sometimes it's worse. It doesn't function like penicillin. That's why all these different types of penicillin-like, as an example, compounds. Anyway, so the main takeaway from this is this: don't make it too complicated. When you look at a bond, if it's A and B scenario, and it's not a carbon-hydrogen, it's polar. That's it. Okay? And then if you want to draw the polar bond, the arrow, where you find its position relative to fluoride and see who's more electronegative. And use a periodic table. You don't have to memorize this value and then draw that arrow. The arrow goes to the most electronegative atom, and the plus sign of the arrow goes to the least electronegative, in the case here, carbon nitrogen. Okay? So that's how we identify this. Now, in general, because there's always exceptions to the rule, I've always stated that there's nothing ever is 100%. But in Chem 130, when you have non-polar bonds throughout your molecule, guess what? You end up with a non-polar molecule. I'm going to repeat that again. If you have non-polar bonds throughout your molecule, overall, all the bonds are non-polar, overall polarity of the molecule is non-polar. There's a difference here. The polar bonds have an effect, the polar and non-polar bonds have an effect on the overall polarity of the molecule. Okay? With polar bonds, in general, if you have polar bonds, you end up with polar molecules. But if the arrows do not, these arrows I just drew, do not cancel each other. This will make more sense here in a second. All right. Equally shared nonpolar bonds. Okay, and that scenario is basically an AB or carbon-hydrogen bond. And then ones that are unequally shared, that scenario is essentially is an AB scenario. Okay, different atoms. Refresh your memory, the electronegativity is the ability of a bonded atom to attract the electrons onto itself. Okay. Depending on its electronegativity, using fluoride as the reference point to figure out which one is more electronegative. Okay. Noble gases obviously do not have electronegative value because their octet is full, and that includes helium. It's not an octet for helium, it's a duet for helium, right? So they don't have anything. So the trend for electronegativity is you got fluoride somewhere top right corner. Right here. And that is my benchmark, and that is where you can use as a reference point when you want to compare the electronegativity of two atoms other than fluoride. If fluoride's involved, no questions asked. Fluoride's the most electronegative element in that particular bond, and that's it, plain and simple, right? So all diatomic elements are nonpolar because they have equal sharing, okay? Carbon, hydrogen, because the electronegativity of carbon and hydrogen is essentially the same, its value, it's considered to be a nonpolar species, okay? And in fact, a lot of oil compounds, a lot of oils are made up of carbon-hydrogen bonds, okay? Carbon-hydrogen bonds. Okay, so times 28. All right, to tell you what, let me let's take a quick break here. And I got almost 2:30. Let's come back at 2:45. All right, and then we'll continue there. All right, any questions so far? No? All right, we'll come back. Okay, well, let's continue here. We're talking about polar covalent bonds. Okay, so most covalent bonds are between two different nonmetals. And one of these is going to hold on to the electrons more tightly than the other, and that's dependent on their electronegativity. Okay, so if we look at bonds like carbon, oxygen, hydrogen, chloride, sulfur, and fluoride, and silicon and nitrogen, all of these are polar covalent bonds, simply because they're two different nonmetals, and they are, one of them has a lot higher electronegativity than the other, okay? So we result in using what we call the polar arrow to designate in which direction that pull is occurring. The arrow points to the atom that's a lot more electronegative, and then the positive side points to the atom that is least electronegative. That doesn't mean it has a positive charge. It has what we, like I stated, a partial positive. So that symbol is lowercase delta, means it's partial. And it's only partially basically because what's happened when you have an equal sharing, there's electron density equal amongst the two atoms. So I can represent that in this means maybe. And so we have like A and A, right? And this kind of a circle kind of represents an equal, it's supposed to be symmetrical, obviously it's not the artist, but if you can imagine it's a symmetrical circle in which the electron density is equally shared amongst A and A. Now, when you have the scenario where you have A and B scenario, and B happens to be a lot more electronegative. Now you can see how the electron density is going toward B, because I just defined B as being more electronegative. Could be the other way around. All right, so here we have carbon fluoride, no questions asked. Fluoride's the most electronegative, so that arrow obviously is going to go from carbon to fluoride with a partial negative on the fluoride side. The bond between oxygen and hydrogen is a lot more electronegative. And so therefore the arrow goes in this case from right to left with a partial positive on the hydrogen side. And between phosphorus and chloride, the halogen, the chloride, is a lot more electronegative. So therefore its arrow is going from, in this case, from left to right, okay? So obviously we talked at length about noble gases. They're just not gonna create any bonds, okay? So FYI side note, beyond the scope of Chem 130, but the big noble gases can react, but it's beyond the scope here in our class. All right. Fluoride, again, restating what we already talked about, has the higher electronegativity. You may be asked to draw the delta notation, that partial negative, partial positive, and the polarity arrow. And you look at it, you look at carbon, oxygen, you look at their position on a periodic table, who's a lot more electronegative, carbon or oxygen, and obviously oxygen is. Why? Because oxygen is closer to the fluoride. Therefore, the arrow goes from left to right in this scenario, and the oxygen has a partial negative. In the case of nitrogen and the fluoride bond, no questions asked. Fluoride is the most electronegative. There's nothing really to look up. The arrow automatically goes from left to right, giving the partial negative on the fluoride side. Okay, keep in mind it's drawn with the nitrogen on the left, but it can easily have been drawn with the fluoride on the left and the nitrogen on the right. Okay, so it just means that the arrow goes in the other direction, that's all. All right, so oxygen and hydrogen, we stated earlier, oxygen is a lot more electronegative. So its arrow goes from right to left. In this case, carbon and chloride, the chloride is a lot more electronegative, therefore it's going from right to left. Now, hydrogen and carbon, this is where students tend to forget. Remember, carbon and hydrogen is the only exception to dissimilar nonmetal atoms where the electronegativity is essentially the same, and therefore no arrow involved here. The pull is equal. Okay, so it's not a polar bond. Okay, all right. Now, question might be asked, which bonds are ionic? All right, well, to be ionic, we have to have a combination of a metal and a nonmetal. Obviously, the first one are two nonmetals. Second one is, again, two nonmetals. And the third one, we got sodium, which is a metal, and chloride, which is a nonmetal. Therefore, this one, sodium chloride, is an ionic bond, okay? And then the fluoride and the bromide are not ionic. So the only one here is the sodium and the chloride, which means that everything else is covalent, okay? There's only two types of bonds, ionic and covalent. Okay? Now, within the covalent, there's a subset. Better way to do it is we got ionic bond, and then we got covalent bond. All right, underneath them, there's two, a subset. One, you either have a polar bond or a non-polar bond. Okay, and that depends on the electronegativity of the two atoms involved in that covalent bond. All right, so everyone else is covalent, and now we go back and we determine that bromine and bromine are the same as diatomic. So we have a non-polar covalent bond here, NPC, non-polar covalent bond. The phosphorus and the fluoride, definitely a polar covalent, because two dissimilar atoms, okay? We talked about sodium chloride already, and obviously the fluoride and the bromide, we have two dissimilar nonmetals, so therefore we have a polar covalent bond. Okay, so no arrow for the bromine. We have an arrow from left to right with respect to the phosphorus fluoride. No arrow for sodium chloride because it's ionic. There's no partial positive or partial negative there. And the one for the fluorine and the bromide, it is going from right to left, okay? If we needed to draw the arrows. Okay, so polarity is very important in chemistry. It has a huge effect on a variety of different things. Okay, so it's something that will show up again as we proceed with the chapters. Okay, consider it as basically a tug of war between bonded electrons, and one's going to pull the electrons more than the other. Okay. All right. Here, you might have a list of things, and they want you to figure out which is ionic, which is polar, and which is the non-polar bonds. We're talking about just about the bonds. And so we can see that we got sodium combination of sodium and chloride. Obviously, metal, non-metal, it's ionic. Hydrogen and chloride is covalent. More specific, it is a polar covalent bond because we have two dissimilar atoms. Hydrogen, it's covalent, but it's a non-polar because the two atoms are the same. Okay, so it's equal sharing going on there with the bond. The chloride and carbon, definitely two different atoms, therefore we have a covalent bond, obviously, but it is specifically a polar covalent bond because of the two dissimilar atoms. Carbon and hydrogen, again, these two atoms, though they're dissimilar, that's the only exception of dissimilar atoms that are non-polar covalent because the electronegativity of each one, hydrogen and carbon, is essentially the same. Okay, oxygen and oxygen, that is simply a diatomic, and all diatomics are non-polar covalent bonds. Then we got potassium and oxygen, or in this case oxide, and that definitely is an ionic. Okay, got a metal, non-metal. And then phosphorus and fluoride, definitely a covalent bond, but more specifically, a polar covalent bond. All right, now, with respect to looking at the bonds, and then from that information, extrapolating to the full molecule and determining, is that molecule polar or non-polar? Okay, and these are things you need to determine, because from that information, then we assign a particular type of force, intermolecular force, to that molecule. And that force depends on whether a molecule is bonded, is polar or non-polar, and that is dependent on the bonds. Okay, so when you have a molecule that all the bonds in that molecule are non-polar, then you have overall a non-polar molecule. Okay. Now, if you have a molecule that have polar bonds that do not cancel out, you end up with a polar molecule. Okay, what does that mean, cancel out? Okay, let me give you another example here. Polar bonds that cancel out because of their position end up as being net nonpolar. For example, what we do is we utilize the polar arrow, because that arrow, we're going to introduce a little bit right now. That arrow is basically what we call in mathematics and in the military a vector. Okay, a vector is a moiety that has both direction and magnitude. Okay, and that means I can say to you north, but that doesn't mean anything, right? But if I say 50 miles north, then you know exactly I'm going 50 miles north, east, west, whatever. It has direction and magnitude. Well, the polarity has a similar thing, and that arrow represents the magnitude or the strength of that polarity. Okay, and it has direction. And so when I have an arrow and I'm pointing it from right to left, okay, I can put another arrow and graphically say that if this has 10 units of magnitude and this has 10 units, well, my overall will be 20 units of magnitude, because both of these are going in the same direction, right? Now, if I have an arrow of 10 units of magnitude going to the left, because that is direction, we're going to the negative side, and I have another arrow going to the right with the same magnitude, guess what? My net is 0, because I got 10 units in the left in the negative direction, 10 units in the right direction. And that is what is happening with carbon dioxide. Remember, we did the Lewis dot structure of carbon dioxide and came up with this structure. Now we take it one step further. If we analyze each bond, and that is on the right side, it's carbon and hydrogen, obviously it's a polar bond. Therefore, we can draw that arrow going from left to right, okay? Because there's a partial negative here and a partial positive on this side. On the other side of this molecule, we have another carbon-hydrogen bond, which also is a polar bond, and the arrow goes from right to left. So results, carbon has a double whammy, has a double positive side, and then the partial negative, I should say, double partial positive side for the carbon, and then a partial negative on the oxygen side on the left. The result is they're both going, have the same magnitude, but they're going in different directions. The result is that even though carbon dioxide has polar bonds, okay, even though it has polar bonds, because these polar bonds cancel each out, we have a non-polar molecule, okay? And that's what we mean. If a molecule has polar bonds, in general, it will be a polar molecule, unless the polar bonds, if it's got more than one polar bond, cancel out, then it becomes a non-polar molecule. If we look at sulfur dioxide, you can see because of the lone pair, and this is how the lone pair has a great effect on things in general, because of the lone pair sitting there in the central atom, it shoves that bond angle to be less than 120 degrees. And what's happening is the arrow on the right, the polar bond from the right is going on the, say, southeast direction. And the polar bond on the left is going in the southwest direction. They do not cancel out. The result is they end up with a polar molecule. Now let's do this. If depends on this example here where I had 10 units to the left, 10 units to the right. Well, if it was say 5 units to the left and 10 to the right, well, wouldn't I end up with a net 5 units, right? Because I got negative 10 to the left and positive 10 to the right. So in this scenario down here, we would still end up with a polar molecule because not all the magnitude got canceled out. So you got to be careful when you look at the molecule. If they're all equal, then they all cancel out. Let me give you an example. Carbon tetrachloride. We got carbon, and we end up with 4 chlorides on this. Now you can go through the Lewis dot structure for this species. This is carbon and 4 chlorides, okay? And what you will end up with would be a tetrahedral configuration, okay? Now, at first guess, you would say, well, I got 4 polar bonds, and you would be not incorrect. You will be correct. I got 4 polar bonds, okay, going away from the central atom, okay? But because of the geometry in the tetrahedral configuration, all of these 4 polar bonds would cancel each other out. So this species, carbon tetrachloride, would be non-polar because they all 4 polar bonds cancel out. Now, if, for example, I were to change, let me erase one of these. And I were to change that and replace one of the chlorides with the bromide. Okay, guess what? I have 4 polar bonds, but there's a different magnitude of the polarity on each bond. And the result of this would be this scenario here, because the magnitude of 3 would be different than the magnitude of 1. So I would still have a net polarity left over, and I will end up with a polar molecule, okay? All right. Now, if I go around the horn and I continue to replace all these other guys with bromide, be polar. I replace another with chloride with bromide, it would be polar. And replace the last one with bromide, guess what? I go back to non-polar because now they all cancel out, okay? And I can do that with either bromine or hydrogen. If I replace that bromide, it was 4 with hydrogen, I end up with a polar bond, okay? So that's how the polarity of the bond greatly affects the overall molecule, okay? All right, so in essence, if the polar bonds do not cancel out, then you got a polar molecule. So to know if they cancel out, you have to go and figure out the Lewis dot structure, which means go through the exercise we just did of finding the general formula to find the geometry, and then identify the polar bonds and see how they are relative to each other and see if they cancel out, all right? To be able to answer that question. So, we talked about carbon dioxide. Carbon dioxide here, they cancel out if a nonpolar species, okay? The fact that this species, this is carbon and 4 hydrogens, the fact that you're dealing with all nonpolar bonds, we end up with a nonpolar molecule here, okay? And it's carbon with 4 hydrogens. That is tetrahedral. You can go through the exercise of figuring out its configuration. This would be an AB4 configuration. It'd be tetrahedral. Carbon hydrogen bond, all nonpolar. We talked about carbon dioxide, where the polar bonds cancel each other out. So we end up overall with a nonpolar molecule. And if we do this one, you need the Lewis dot structure, and I'll let you run through that. It's very similar to ammonia, and you end up with this structure here. And the fact that you got a lone pair of electrons in the central atom automatically would tell you, hey, I got a polar molecule, plain and simple, plain and simple. You can go through the analysis and figure, okay, I got a polar bond here, 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 and then realize that that lone pair, you know, this not tetrahedral. Those polar bonds will not cancel out because of the lone pair. I got a polar molecule. Okay. All right. So here we go. All right, so we did do the water and we did ammonia, okay? And water having 2 lone pairs is extremely polar species, very polar molecule. Ammonia, again, with the lone pair in the central atom, very polar species, okay? So with that being said, congratulations, folks. We're about halfway done, right? Almost. All right. Any questions? Because what I want to do is I want to complete this chapter 8. Okay? Because we have the next exam coming up on Tuesday. And it's a short chapter. It doesn't take very long. 24 slides, actually a little bit less. Okay? So this deals with nomenclature. I have been introducing nomenclature as we proceeded. Don't forget about the nomenclature exam, unlimited attempts. All right, so knock it out as soon as you can. You keep in mind the 21st is the day that everything shuts down. So if you have any late assignments, once the 21st, I believe 11 p.m., everything shuts down. So keep that in mind because the semester is slowly showing up. All right, so we did mention earlier about knowing the first 20, at least the names and symbols for the first 20 elements of the product table. But then also we added some, I think we had a few more here. We got Ba, which is barium, okay? We got barium sitting here. Co, which is cobalt. I for iodine. Cu for copper. We got Fe for iron, Pb for lead, Hg for mercury, Ag for silver. These two get confused a lot, the Hg and the Ag. I don't know if I can tell you that, tell you what you can do to differentiate, but Ag is silver, Hg is mercury. All right, then we got Au for gold, Zn for zinc. This one, a little bit different. It's called stannous, S-T-A-N-N-O-U-S, or we can use the word tin, okay? So, this morning when you were brushing with your teeth, you may have been brushing your teeth with stannous fluoride, okay? Check that out. So you might check the label on your toothpaste. You were brushing your teeth with a tin ion. And then we got strontium, nickel, bromine, chrome, manganese, and cadmium, okay? All right, now, ionic compounds, combination of metals and non-metals, okay? Covalent compounds, again, where it's a rehash, non-metals only, also called molecular compounds, okay? We have monatomic ions. These are ions that only have a charge, sodium, chloride, calcium are some examples. And then we introduce you to the polyatomic ions today in that table, okay, where there are two or more atoms, specifically nonmetals, that are combined, but the whole molecule has a charge, okay? So be familiar with them, at least be able to identify them. And the thing to remember about the polyatomic ions is we keep them together as a unit. We don't separate them, okay? Now, I've been using the term, the charge on this atom and the charge on that. I'm going to start switching over to the term oxidation state. And let me explain why. When we deal with ionic compounds, the charge is pretty straightforward because they literally do have a charge. You have a full positive or full negative, okay? When it comes to covalent compounds, we don't have a full charge. We have a partial charge. We introduced that today, okay? So it's not really true to say in covalent compounds that we have a charge. And so to make it more technically correct, the term oxidation state is used, which is basically what charge they have, if it's ionic, if it's an ionic compound, or what is the partial charge, if it's a covalent compound. All right, it's basically what you're saying here. Okay, all elements, as I stated, have a charge or oxidation state of 0. Okay, and why is that? Because we have an equal amount of protons and equal amount of electrons. The net is 0. Okay, and so the elements that have either lost or gained electrons now are ions. Okay, and some of these ions have fixed charges. Now, if you recall, I did introduce this in this periodic table here. We had the sweet 16, remember that? I've got them circled. The first column 1 and column 2 are 12 of the elements. Column 1 has always have a +1 charge. Column 2, always, group 2A always has a +2 charge. And then I added 4 more. Aluminum always with the +3, zinc with a +2, silver with a +1, and cadmium with a +2. These 16 always have a known charge, okay, the sweet 16. And that being the case, once we know they have a fixed charge, then when we name the compounds, if they're in the compounds, we don't use what we're going to learn about our Roman numerals. And so sodium chloride is NaCl, strictly sodium chloride. It won't be sodium 1 chloride. So on and so forth. So that's why we need to know. That means that all the other metals other than 16 have a variable charge. And for example, copper can exist either as a +1 or a +2. Iron can exist as a +2 or a +3. It depends on the reaction and conditions to give it whatever charge. We know about metals, lose electrons, become cations, okay? We talked at length about these metals and their particular charge and what charge they would have, or oxidation number. Group 1 +1, group 2 +2, group 3 +3, okay? And those are the sweet 16, which means that the other metals other than 16 will have a variable charge that can go from a +1 to a +9, all right? And to distinguish those metals, we use Roman numerals. So you would see, for example, the name iron, Roman numeral 3 in parentheses. Make sure it's in parentheses. And the Roman numerals in uppercase, okay? That is the correct syntax, the format to write the oxidation state of that metal. That Roman numeral pertains only to the metal, has nothing to do with whatever follows, okay? So copper +2 is written as copper parentheses Roman numeral 2 in parentheses. Iron 3 is written as iron parentheses Roman numeral 3 in parentheses, and lead there you can see parentheses IV and parentheses. And so whatever in the parentheses again pertains to the metal only. That's for the ionic compound. Nonmetals, as we stated, gain electrons. So group 5, we end up with a -5, -2 for group 6, and -1 for the group 7. Not only that, the name changes, okay, when they become anions. So sulfur becomes sulfide. Oxygen becomes oxide. Now the term oxide remains oxide, be it in ionic compounds or be it in covalent compounds. So you can have sodium oxide, or you can have carbon dioxide. You see that? The name stays the same, be it in whatever type of compound you're using. Of course, noble gases don't have anything. All right. So let's begin learning the format and the names of ionic compounds. Now remember that ionic compounds are made up of ions that have a charge. And when we put them together, they must equal 0. And that's important information because it helps us either to create the compound or to name the compound. So one general formula to remember is this. Maybe one way to look at it is this way. Okay, the number of cations plus the number of anions must equal the charge of the compound. And this is a very good generic formula to have. Normally, the charge of the compound is 0, 99% of the time. But you can have a polyatomic ion that may have a charge, and you put that charge right there. So you can calculate, for example, the oxidation state of sulfur in the sulfate, because we don't know what sulfur is, but we know that oxides always have a -2. Here's the overall charge of this molecule. Or we can calculate the oxidation state of sulfur in sulfur trioxide. Here's a neutral species. So in this case, the charge of the compound is 0, okay? So this is a good general formula because there are some homework problems that they give you the charge of the molecule, the compound, and they ask you to calculate, let's say, what is the oxidation state of sulfur, okay? And use this generic formula to calculate that. All right. So we have the polyatomic ions. These are in your table, okay? If we need more than one of these, always remember to use parentheses, okay? We keep them together as a group. They have a very specific name. they don't, the name doesn't change, okay? All right, so when we put them together, we got to add them so it equals 0. For example, combine sodium and nitrogen. Well, to do that, we have to first write them in ionic form. We know sodium has a +1 and the nitrite has a -3, right? So we got sodium with a +1 and the nitrite with a -3. This tells me that I need 3 sodiums to cancel out the -3 charge of the nitrite. So that 3 I wrote here becomes the subscript for sodium. So that is the formula for sodium nitrite. Okay, sodium nitrite, not sodium nitrogen, because now nitrogen became an ion. And once the nonmetal becomes an ion, the name we get rid of, we change this name to the IDE ending. Okay. All right, let's do this one. We got sodium and sulfur. Well, similar now process. Sodium +1. The sulfur is in group 6, right? So that's why it's important we know what group it's in. We also need to know, based on its group, what is its charge once it becomes an ion, and it's a -2, meaning group 6, it needs 2 electrons to get that magical 8. All right. So now we got a +1 and a -2. That tells me I need 2 positive sodiums to write the formula, and there is the formula. Okay. The name sodium sulfide, not sodium sulfur. Okay, but sodium sulfide. All right, we have magnesium and oxygen. Well, step 1, write them in ionic form. Magnesium is a +2, a metal, it would have a +2 charge. Oxygen, like sulfide, is a -2. Okay, now we can put them together in the 1-to-1 ratio, fine, because I got a magnesium ion is a +2, the oxide ion is a -2. All right. So it's simply a 1-to-1 relationship. So that is the formula for magnesium oxide. Okay. All right. Potassium, write them in ionic form, as a +1. Phosphorus, okay, it's a group 5. We've got lightning going on side. It's a group 5, so it will have a -3 charge. Okay. That means I need 3 potassiums for every phosphide. Right? So its formula becomes K subscript 3 phosphide, potassium phosphide. All right, now this is a little more challenging, okay, but doable, and I'll use some analogies here. Let's first write the calcium ion, okay? Calcium ion, which is a +2, and then the nitrogen becomes nitrite, which has a -3. Now, unlike the examples we were just doing, now we have dissimilar charges, right? And so what I got to do here is I got to find a common charge. Much like in mathematics, when you take a fraction, like 1/3 plus, let's say, 1/4, you know, if I want to add these 2 fractions, what do? I write the common number, right? Common denominator, right? In this case, 1/3, 1/4, common denominator could be 12ths. I convert the 1/3 to 12ths and the 4th to 12ths, and then I'm able to add it. Well, similar here. My common number here between the +2 and the 2 and the 3 is 6. Okay. All right, that's the common numbers, which means that I need 3 + 2 calciums to give me at 6, and I need 2 -3 nitrites to give me at 6, in this case, -6. So total, I got a +6 here and a total -6 here, right? They cancel each other out, which is perfect. So that becomes a subscript. So I got calcium 3 and then N2. That is the formula for calcium nitrite. Okay. Something else to note to help you out as a guide. Notice that the charge of the cation becomes the subscript of the anion. Notice the charge, the value, the absolute charge of the anion becomes a subscript of the cation, okay? And so I want to, when I get dissimilar charges, I want to get enough of each so I have a common number so I can cancel out the total charge, okay? Common number. So that is the formula for calcium nitride. Notice I haven't been using any Roman numerals. Why? Because every metal here is the one with an exact oxidation number. So no Roman numerals, simply straightforward. Calcium nitride, potassium phosphide, magnesium hydroxide, sodium sulfide. All right, aluminum chloride, aluminum is a +3, okay? And the chloride is a -1, which tells me I need 3 chlorides for every +3 aluminum. Our formula becomes AlCl3. Okay, zinc has a +2 and the iodides have a -1. So its formula will be zinc I2. We all see that? I didn't write that down. Zinc always has a +2. And the iodides, all halides have a -1. So I need 2 of those. So I need 2 halide iodides. Okay, now we got the variable oxidation state. So that Roman numeral tells me that I'm dealing with copper +2, okay? And the oxygen is a group 6 nonmetal. It will gain 2 electrons as a -3, just like the sulfur did, okay? So I got copper +2 and oxide with a -2. Straightforward 1-to-1, and that's the formula. Okay, now I'll write down all the names here when we're done. All right, here we have lead 4, so we got lead +4 because of the Roman numeral, and we know that every oxide is a -2, so I need 2 oxides to cancel the +2 of the lead. Okay, so its formula becomes PbO2. Okay, all right. With that said, we got sodium sulfide, magnesium oxide, potassium phosphide, calcium nitride, aluminum chloride, zinc iodide, and we got copper, Roman numeral 2, oxide, and then finally lead, Roman numeral 4, oxide. Okay, now, with that being said, you can mix and match here. You could take that sodium and hook it up with the oxide or the phosphide or the nitride or obviously the chloride or the iodide, okay, and do the same with magnesium. So you can mix and match here. So you're starting to build up your database of the different compounds that you're making, okay? The takeaway from here, from this exercise is this. Given the elements, you got to convert them to the ions, which you use the periodic table to help you to figure out what charge they have. Then from the charge that they have, the oxidation state that they have, determine how many of each you need so that when you combine them, you end up 0, okay? And that's the formula. And then the name, if the metals are a member of the sweet 16, no Roman numerals. Okay, straightforward, whatever the name is of the metal, and then obviously the anion changes to the "ide" ending. Okay, if it's any metal part of the non-sweet 16, you have to use the Roman numerals. Okay. Now you can reverse it backwards. Let's say you're given this formula right here, PbO2, and you didn't know what this was, right? All right, so let's say you're given this. Okay, so remember that formula I gave you? I said, I don't know what Pb is, that's the question mark, but I do know that plus, I got two oxygens, each one is a -2, and that is equal to 0. I can create a not so complicated algebraic equation where Pb minus 4 equals 0, and I solve for lead. So Pb equals plus 4. Okay, so if I'm given the formula and I don't know, and they ask me, what is the oxidation state of lead? I can calculate it using that equation of total number of cations plus the total number of anions equals the charge of the compound. In this case, the charge of the compound was 0. Okay? And you always will know the oxidation state of one or the other. If you don't know, if you're looking for the oxidation state of the cation, you would know one or the other. For example, sulfur trioxide. All right. I don't know what sulfur is, but there's 3 oxides. Each one is a -2, right? -6 equals 0. So sulfur is a +6. So in this state, sulfur is a +6 oxidation state. See how that works? All right. So, not important. Make sure the charges are correct. All right, what I'm going to have to do, I was hoping to get this knocked out, but I guess not. I'm going to have to move the Tuesday exam maybe to Wednesday so I can finish this up. This is only like 6 slides. So I recommend that you go through the slide to the end of it and finish it up. There's only like 9 more slides or so, 10-ish, 12. Okay, and knock it out, and then on Tuesday we'll come back and finish this up, and then I'll move the exam number 3 over to Wednesday, okay, to give you the time to look over this, okay? And yeah, of course, yes, of course, and the homework, and remember, I won't make anything due until we get that chapter completed. But I took a little bit longer than anticipated. So, but I'll give you, I'll move it over and go from there. If you want to maintain and take it on Tuesday, let me know and I'll keep it open for you. What I'll do normally is I would keep the date open when it's available, and then the due date will be the next day. So if you feel comfortable and you want to knock it out anytime between Tuesday and Wednesday, feel free. Okay, fair enough. All right. Yeah, and I will definitely switch the homework over. Yeah, don't. If I ever miss it, don't freak out. I missed it. I'll catch it. All right, let's stop it here and make some notes for myself.